Welcome back, and I'm going to be looking into the link between many algorithms in use today, recursive algorithms used in a number of areas in signal processing and in computer science and in mathematics, and the link to control systems using negative feedback, in other words. This is something I've been interested in now for actually quite a long time, but beginning to put it all together. I'm by no means the first person to have looked at this. The history of this goes back probably to the 1950s even, but it doesn't get a huge lot of publicity for some reason, maybe because it's a control area and it's not an area that everybody's interested in. Let's think about control systems for a minute. And when you think about control systems in the traditional sense, whether that be in so-called classical control systems that you study in electrical engineering or a mechanical degree, or it'd be so-called modern control systems, which is like state space and so on. But when we think of them, we normally think of things like this, hard disk drives, servos for that, very fast mechanical servos, control of motors, machines, there's an induction motor here, control of missiles, which is getting into the state space and nonlinear control and so on. That's coming from the early 1960s and late 50s. And robotics, more modern robotics, and walking machines, machines of course now that can run and jump and do a whole host of things. That's what we normally think of. We think of these engineering applications because control engineering, or as we call it, or control systems, is normally studied by most engineers, even chemical engineers, controlling processes for various chemicals and so on, liquid levels and the like. But of course, control systems also appears in mathematics. It's just a theoretical topic. But what I'm looking at today is more not in the normal mathematics of control, but how mathematics itself has algorithms which turn out to be feedback control systems, even unbeknown to the people who invented them. So let's see what I mean by that. Well, here's some more historical ones, of course, going way back. This is machines, the James Watt flyball governor to control the speed of a steam engine. Of course, that's considered to be probably the first ever feedback control system, barring a clock, which clocks have a regulator for the speed, of course, for the time. So arguably a clock could be before that. This idea, Watt also got this idea, I believe, from mills that were grinding corn and so on. There were similar sorts of ideas there, and this kept the steam engine at a constant speed, so it didn't go running off. That's another story, however. So that's what we normally think about. Well, what about control systems applied to signal processing or early mathematical methods? So here's our normal control system. I've drawn this in discrete time in Z transforms. We can do the same with Laplace, or you could use j omega if you wanted to in frequency domain. So this is a linear time invariant system. We've got our input and our output. So the output's trying to follow the input as closely as possible. We've got our system, whatever that may be, that we're trying to control, and we have to have this compensator, because if we just put feedback around it as it is in a raw state, it won't behave the way we want it to behave. The output won't necessarily follow the input. I mean, it maybe try to follow the input, but it'll be perhaps too slow, so we want to speed it up. We want to speed it up. When we speed it up, rather, we normally increase the gain, and when we do that, it becomes oscillatory, let's say, and then so you've introduced another problem. So we need to understand the science, if you like, the mathematics behind it, and that's of course where all the engineers at Bell Laboratories, among other people, designed methods like Bode plot and so on, and other methods, of course, at the time, like root locus and Nyquist diagrams and so on. But Bode plot's still around still very useful. The D here is a disturbance that comes in, so if you're trying to control the speed of a motor, for example, this would be something trying to slow the motor down. There could be a ship steering system, and then the wind's trying to blow you off course, and the control system has to keep the heading. That might be the heading here, and it's going in that particular direction. And what you'll find is that a lot of the algorithms that we're looking at will have a system which is just a pure integrator with a gain, or integrators, when it's sort of multi-system, multiple input and output. Here's the equations associated with that. Cg over 1 plus Cg, that's the common one, plus this times the input, plus 1 over 1 plus Cg times the disturbance. So what that means is, if the magnitude of either of the plant, C or G, or both of them rather, is very large, the effect of the disturbance becomes small and gets swamped by this. And of course, if Cg is very big, then Cg is going to be greater than 1, and so you get Cg over Cg, so that y goes to r in the limit. But this only happens, of course, if you can keep the thing stable. You can't just stick anything in there. So you've got to keep the poles of 1 plus Cg in the stable region of the plane. So if it's in the discrete domain, it's got to lie within the unit circle. If it's in the Laplace domain, it's got to lie in the left hand of the S-plane. And how we do that, of course, we can either do that using state space methods, we can use Bode plots, we can use a whole host of methods. Usually if there's only one input and output, we can just use a Bode plot or something quite similar. But there are a whole host of methods in the literature available to us to do something like this. And now usually the compensator that we pick in engineering is either one of two. It's normally a PID type controller. That's the one used common in industry. Also for electronic systems, which is very similar to a PID controller, is a lag lead controller. And it's kind of the same thing, more or less. Talk about it in a minute. So yeah, this is an amplifier with feedback, like an op-amp. Same sort of thing. Forward path A, feedback path A, beta. Beta is usually less than 1. It's a resistor divider network, and what happens here is that A times beta is greater than 1. The output over the input is 1 over beta. So what that we can do there, provided it's stable again, of course, is we can provide a resistor network, which is beta, to get a defined closed loop gain, which is 1 over beta. So if beta was 0.1, we can get V out over V in is, say, a gain of 10, or whatever we want. Standard operational amplifier. The concept of the feedback after the time of Maxwell, Maxwell was the guy who analysed, James Clerk, famous Maxwell with the electromagnetic theory, analysed the stability of governors back in the 19th century. It's a little bit hard to follow his paper because it's all differential equations. It wasn't using Laplace transforms, it wasn't algebraic, it was purely differential equations. But he does touch on things like closed loop characteristic equations, although he doesn't necessarily use that terminology. Whereas Black was on the ball here with amplifiers. He, with his patents in 1937, he understood that you could put feedback around an amplifier. What he probably didn't know at the time was how to make it stable. He knew that you could do this, and so you could get a predefined gain on an amplifier. On valve amplifiers at the time, you couldn't necessarily design stable gains. They'd sort of wander around with temperature and so on. That being the disturbance that we talked about earlier. This bit here. This has been the disturbance of the system coming in. So it's getting rid of also in noise as well, because the noise reduces when you do this. So Black did a simple equation, this one here, to show that you get that. But what he didn't really probably understand too much is stability, and some of his colleagues like Bode and Nyquist sorted that out. So strange that they were all working at the same place. The story goes that Black was crossing the New Jersey Bridge or something when it came upon him, and he stopped at the other end or something to get, because New Jersey was where the Bell Labs was, and he stopped the car at the other end, and he wrote some notes down, and those notes are still alive and around, and it looks something like this, with a and a beta and feedback. His colleagues kind of laughed at him when he gave this, told them about it, because they said, well, what you're trying to do is take a very high signal here at the output and feed it back into the input. Doesn't sound like a very good idea to us, does it, to do that? But he was proven right that you could do this, in fact. Now, here's a situation where we've got a multiplier in the feedback path with an integrator in the forward path. So this is continuous time. So I haven't written it as a Laplace transform because it's got a multiplier in it, so it's kind of non-linear in a way. So tend not to, I know this is time domain as well, so we tend not to mix Laplace with time domain things, so just write it as like an integrator as it is, and again k. And it's been known since the 1970s, at least, probably earlier, that if you put a nonlinearity in the feedback path of an integrator, and isn't the integrator normally being an op-amp, an analog op-amp, because the op-amp behaves like an approximate integrator, not quite, but it has a high, you can have a high gain anyway at low frequencies. So you can put some kind of dynamics in here and a multiplier in the feedback path. So this multiplying W by itself, I've just written it like that. So that's a squarer, x squared if you like, in the feedback path. And it's been known for some time that if you do that, then what you get out here is the opposite. You get a square root. So if you put a square law in the feedback path, you get the square root, provided you can keep it stable. And that's been known. So any function in here, you get the inverse. And the analysis is here, a very simple analysis. The error is r minus some function of the output, and you want that error to go to 0, like any control system, so that the output would track the input, but it's not actually going to track the input because it's not linear anymore. But anyway, so if E does go to 0, then R must go to this function f of c of t. So c of t, the output, must be the inverse of R. So you get the inverse of the input. So that, for example, if you put a number in there like 2, you would get the square root of 2 coming out, and you do. And so you could build an analog circuit which give you the square root, and in fact that has been done. I may even remember when I worked at GEC, them talking about a square root function for, I think it was one of these fast lifts or elevators to lift coal in a coal mine or something, was to get it to decelerate, because it goes at a hell of a speed. To decelerate down to rest, they used a square root function. So it was an analog in those days, so they would have used that. But being a student, I didn't fully understand all of that. So anything you put in there, you can get the opposite of it, but the chances are it won't be stable in most cases anyway. If you put an x cubed in there, you're going to end up with problems, but you can put an x squared and get away with it. So just have a look at integrators, because this is an integrator. In the analog world, there's a normal integration like in mathematics, and in that's its Laplace form, k over s. I should have put a k in there, of course, for gain, but you can make it 1 if you like. And in the digital world, it looks like this. There's its z transform, k over 1 minus z to the minus 1, if you understand z transforms. But it looks like this in its difference equation form. Yk plus 1 equals yk. So the new value is the old value. And those of you that have made up PID controllers will recognize that straight away. It's like a thing in software, something like what is it, x plus plus, the y plus plus or whatever. The new value is equal to the old value plus an input. So k times x being the input here. K is a gain, which we can talk about later. It depends on the bandwidth of the loop and so on. So what you actually see in real life is algorithms of this form appearing in the literature. You can spot them a mile off. Yk plus 1 equals yk plus some kind of gain. Often that gain could be some other vector or something, and y could be a vector as well, times an error. And the error itself could be a vector or a scalar or whatever. It could even be a matrix of errors depending on the problem. So we can recognize integration very easily just by looking at algorithms like this. You know, hang on, that's an integrator, and that's an error. So that looks like a control system. And just it's a sort of side issue, but what is of importance is this very famous person, Cauchy, who you would have come across when you studied Z transforms and integration around the Z plane and so on. The so-called, there's a Cauchy-Riemann conditions and the theory of residues. He wrote a paper in France. He's French, in a French journal, Academy of Sciences, October the 18th, 1847, which I've looked at. It's a very short paper indeed. I mean, it's I think it's just about a paragraph, really. Almost like it's almost like he didn't even want to bother with it, but it was on what's called the gradient descent method, and that's an incredibly important area nowadays when we've got neural networks and so on, artificial intelligence. These gradient methods that work in a way which I'll show you here. They sort of find that you've got some kind of so-called convex quadratic function, and you're finding the way down to the bottom to optimize the function. And this is something that invented by Cauchy, and he obviously never realized the importance of it, I think, because I don't think he pursued it that much. I mean, I might be wrong, but others, of course, did. This is this gradient descent method written in continuous time, which you don't really see very often. Is that the rate of change of the output is constant minus a constant times the gradient. Now this means that if you were, it's often explained in this way, if you're standing on a hill and there's fog and you're trying to get to the bottom of the hill, well, I mean, of course, the best advice is probably just to stay put and camp overnight, but if you wanted to get down is to look at, take steps, and where the gradient is the steepest, you go in that direction, and then you take another step and look where the gradient is, and where it's at the steepest, you move in that direction, and you get down to the bottom of the hill the fastest way. I wouldn't recommend it because it could be a sheer drop and you end up dead. But anyway, that's the theory behind steepest descent, and it does work very well. So this derivative is the actual gradient of the function you're trying to go down, and it's approximated by a differentiator here can be approximated by this Euler integration, wk plus 1 minus wk over t. And again, if you've implemented a PID controller, you'll recognize that it's a difference, first difference. It's the simplest form of differentiation you can get. You can get more complicated approximations. T is the sampling interval. We normally make that 1 because unless we're looking at it as a real control system in terms of frequency and bandwidth, it's normally kind of all normalized to unity sampling. So this is the discrete version where you normally see it. It's wk plus 1 is wk minus mu. Mu is like a gain times the rate of change of the output, which is the gradient. You've got to watch what that mu is, because if you make it too big, that's like having too big a gain in a control system, and it goes unstable. And once again, we recognize integration here. Well, it's obviously integration because that's differentiation, but we recognize integration because we've got this wk plus 1 is wk. Now, unlike here, where a simple integrator, that's a scalar, let's say, here this is the whole vector, or it could be a scalar, of course, as well. But that's the steepest descent method, and it obviously is a control system. And just by the way, you can replace that differentiator with a more accurate differentiator, which is the trapezoidal differentiator, and what you get is trapezoidal integration, of course. It still looks very similar, but you've got an extra term here. You've got you've got differential dj by j is the cost function by dw, and dj by dw k minus 1, the previous version. And you do get a slight improvement in doing that, but to be honest, it's not an enormous improvement. So obviously, steepest descent, or a gradient descent rather, you've got to be careful because the method of steepest descent is not the same as gradient descent. I think there's another thing in mathematics. So we call it gradient descent, really. It's really this integrator with feedback around it. If you can actually do some analysis, and so it's just a control system, and we'll come to that again. And here's another common control system that's used a lot in signal processing, and it's the least mean squares algorithm from 1960, or the stochastic gradient method. Now it is based actually on steepest descent, on Cauchy's work, but a slight extension of it. It was made by Woodrow and Stearns, I think it was, in their paper in 1960. So you've got to understand it. It's a little bit tricky, but basically all we're doing here is we've got an unknown system G. We're driving it with some known input, let's say white noise. I'll explain in a minute why it's white noise and not just any other input. We have our LMS algorithm here, and we have an error. So again, it's feedback. We have to define two vectors, one which is the regressors of the input, that's to say the input at time k minus 1, and so on up to k minus n. So you have to pick n is the model order that you're trying to pick. If you're trying to fit a second order, n would be 2, a third order would be 3, and so on. And you can only model here a so-called finite impulse response model here, which it'll converge to the LMS, not an infinite impulse response system. So you write the output as x transpose w plus v, and you do an analysis on that, and you end up with this algorithm, which is the least mean squares algorithm, which is in all the literature on Wikipedia and so on. And mu is once again a gain. Well, I would call it a gain, but the mathematics it's called the step size. And there's a whole load of analysis around what maximum value to make that. It's just quite interesting. A lot of people just pick a small value, and but if the system itself is changing with time, in other words, this unknown system is changing these values, the parameters are changing, then that can lead to problems if mu is fixed. Anyway, we've got an error and we've got an update, which we've got an integrator in the loop again with feedback around it. I'll just briefly just show you a simulation of LMS. You probably find that in lots of other videos, but the least mean squares. Here's an unknown system, 1 over 1 minus 0.5 z to the minus 1. And if you do, say, long division, or a power series expansion, you'll find that can be written like this: 1 plus 0.5 z to the minus 1 plus 0.5 squared, 0.25 z to the minus 2 plus 0.125, and so on. It gets smaller and smaller and smaller. That's how you can approximate a so-called infinite impulse response filter into a finite impulse response filter. But we can find these things. If the system was like that, I mean, I'm picking an ideal case here because it's going to be an analog system the real time will be an analog system, and so you're estimating approximation to it. But the classical MATLAB type algorithm is here, where there's our 1 minus 0.5, that's our denominator, that's our numerator, it's 1, and I've just made 4 terms, so I should be getting 1 minus 0.5, 0.25, and some other terms. So it should be 4. We call these weights or parameters that it's estimating, and I'm just running it for 1,000 samples. So I'll just type LMS and see what should happen. So this is the error. Like any good control system, it's going, well, actually it's the mean square error, not the error. Sorry, I'm going to be careful here. It's a mean square error, not because the error actually is positive and negative. So it'll look more like something oscillating between positive and negative and going down to close to 0. Here's our so-called weights: 1, minus 0.5, 0.25, 0.125, and so on. We can make these smoother by increasing the step size. I've just made mu, I don't know what I've made it, 0.1 or something like that. I can increase the number of weights, so we approximate it to a larger. Let's make it 8 and see if it takes that. Still working. And you see it looks smoother there. There's 8 values now. And the reason for that is because as you increase the number of weights, the kind of optimal value, the maximum value for mu goes down, and so the you get a higher overall gain in the loop. The loop gain is determined also by the number of weights, and so that's why it looks a little bit smoother, because it's got a higher bandwidth, if you like, the loop. And if I reduce the number of weights, it would look more noisy. So if I made it, let's say 2 weights, so it was only 1 and minus 0.5, it should look quite a noisy estimate. Yeah, there it goes. It's quite a noisy estimate. But on the other hand, I could, if I was to increase mu, make it say 0.1, that's much bigger, assuming it doesn't go unstable. Then it should, actually I made it too big there. That's what happens when it goes, it'll eventually go unstable if I make it bigger. We'll make it 0.02 or something like that. Oh, I can't remember what it was before. 0.7, let's say. Should actually be smoother. Oh, it's not actually going to get very smooth. If I make it very, very small, on the other hand, it will definitely get smoother. Actually, that's what I should have done. But it might not converge in the time given, because I've only given it 1,000 samples. Ah, there we go. So it's much smoother there. Increasing it is the wrong thing to do there. It would make it faster conversions, but not necessarily smoother. So you've got to watch the value of the gain, and there are ways around this by using what's called normalized least mean squares, where it kind of normalizes itself, and you don't have to worry about selecting the value of mu. And you have to do that. I mean, I've implemented this in real time a number of times, and you have to be very careful unless you make it the normalized version of, in other words, where mu varies. It's really, you are in danger of being unstable. So LMS is a kind of control system with all sorts of variable things in it. This is an extension to LMS, so we've put a trapezoidal based integrator, integrator in rather than an Euler integrator, and it you notice you get an extra term on there. I published this back in 2010. It doesn't give you a huge advantage, to be honest. I have got some a paper written on that here somewhere. Let's have a look. Ah, yeah. So you only really notice the difference if you when you've got time varying weights, really. If it's constant weights, you don't notice the difference. I'll come back to that. So this was somebody who realized that back in 1978 that LMS could be written in continuous time rather than discrete time. And somebody analyzed it in 1989. I had a go myself, and I came up with this block diagram for LMS. U here is actually our X here. I just didn't want to redraw the whole diagram. There's our integrator, but it's a matrix of integrators rather than a single integrator. So that's our plant or system, and the rest are all sort of time varying things. And what you can do is you can compensate the system like a normal control system to get better performance. But what a better performance would you actually want? That's the question. What are you trying to do? Would you want to try and make it faster? You can't really do that, but what you can do is you can make it better at tracking time varying weights. And time varying weights isn't quite so common when you look at the literature. They normally have constant weights, but in real life it can be that systems vary all over the place. And I was looking at particularly at difficult cases where the weights were changing in a ramp formation, and that was deliberate, because if you think of control systems, they can follow steps, they can follow ramps and perhaps parabolas, and how they do that depends on the type of the system, whether it's a type 0 to type 1 or a type 2 system. So I deliberately picked difficult types of weight variations. So you can add a second integrator to the loop, and if you stabilize it, you stabilize it in this way. This is called the symmetrical optimum, where you have two integrators and then one integrator, then two integrators. So you have minus 40 dB per decade, minus 20 dB per decade, and minus 40 dB per decade, and you get this is our bandwidth here, where you cross over frequency, and you get a phase margin, a maximum phase margin of 55 degrees or so, depending on the ratio of this upper to lower frequencies. That's called the span ratio. You can read about that in my book called Feedback, by the way. So we end up with double integrator LMS, which is kind of an improvement. I'll say kind of because it's got disadvantages as well. Well, what we've done here is we've added, instead of one integrator like an ordinary LMS, we've got double integrators here. So there's 1 minus z to the minus 1 squared. I don't know if you can see that. And then I've got a phase advance, that's what's doing the making it move to from minus 40 to minus 20 dB per decade. Everything else is the same. Oh, where is it? Oh yeah. And another author didn't look at double integrator LMS, but looked at a more compensators of this form. Famous guy called Glover in 1979. High order algorithms for adaptive filters in the IEEE transactions. And actually that makes a lot of sense, because it turns out when you have two integrators, it's quite hard to control it, and you end up with, if you're not careful, you can end up with oscillations and so on. And I can show you some simulations of that. So this is with 20th order FIR system. You're trying to estimate 20 weights which are all ramping up and then ramping down again. And so if this is the 20th weight, just to give you a good example, that's a ramping up, ramping down. So LMS and the trapezoidal method behave very similarly. They can't really track it because that's a type 1 system, and a type 1 system with a single integrator cannot track a ramp. If you remember from your basic controls theory, you need two integrators in a loop to be able to track a ramp. The trapezoidal LMS gives you slightly less mean square error, but it's not a huge amount in it. But notice this is a classic. It doesn't behave like a deterministic system where you'd normally find a constant error all the way, because it's random inputs, so it's not quite like that. But what happens when you put two integrators in is, well, there's still an error, but it does track it a much better, particularly here on the downward path for some reason. And so, where's the double integrator one? No. Oh, sorry, this is not double integrator. This is just, I've just increased the bandwidth. Yeah, so this is with a higher, in other words, I've just increased the gain of the loop. So, but when you put two integrators in, here's the one. then you're ending up sometimes, at least, with DILMS, that's double integrator LMS. You're ending up with a zero error, but it doesn't. It's not all the time, so it doesn't behave quite like a deterministic system, where deterministic system would be an error and then it just sort of makes its way to zero, and it's kind of like that, but it hasn't had a chance quite to settle down because the weight's changing in the other direction, so it's wobbling about and it's making its way down to a smaller error there. So that's with two integrators. You can see how you can improve the loop, but for a lot of practical problems it's really not of great use. It's of great theoretical importance, I think, but not of much use in a lot of real problems because of the stability issues. You really need to keep it stable. There are lots of so this is just explaining there are lots of ways of compensating in the classical sense. First of all, you can have just a pure integrator in a loop, and that gives you 90 degrees phase margin. It's got a minus 90 degrees phase, so it's 90 degrees phase margin. It's perfectly stable. You can stick on a roll-off at high frequencies. This is like a pure lag here, a pole at high frequencies, and that reduces the phase margin, but that would reduce the noise at high frequencies, any noisy terms. That's called momentum, the momentum method. You see that in many papers. Let's introduce a momentum term, and they're introducing an extra term in their algorithm, and it turns out that's what it's doing actually. It's putting in engineering terms, it's putting a low pass filter there at high frequencies, so it should improve things but decrease the stability a little bit. And you've got to watch again for your weights here. This is analog, so there's no restriction on bandwidth for a pure integrator in theory. In a discrete system, you're limited by the half sampling rate, so you can't just increase the gain and make the bandwidth anything you like. It has to go. The bandwidth here needs to be something like, realistically, maybe a tenth of the tenth of the sampling rate. Sorry. So if you sampled at 10 kilohertz, you might make the bandwidth 1 kilohertz, and the half sampling of the Nyquist frequency is 5 kilohertz. Then other things you can do, like here, you can put in a PI controller, so you can increase the gain at low frequencies. So what this will enable you to do would be to follow ramping type weights, which are more time varying problems. So you won't get any advantage at all if the input is constant, because with a pure integrator you get zero steady state error anyway. Two integrators you get zero steady state error, exactly the same. In fact, you probably get slight overshoot maybe even with this. But if you're tracking something that's ramping or changing with time, like PI controller is not a bad idea. You can do something similar. This is here up to this set of frequencies. This is very similar, but then it goes down. It's minus 40, then it goes to minus 20. So that's putting in what's called a lag compensator. If you look in the control textbooks from the 1960s and the 70s, you can look in my book as well. That's a lag, and then this bit here is a lead. So it's a lag lead compensator, sometimes used in amplifier design and so on. A lag lead is like a PID controller a bit, except for it's not a pure integrator at low frequencies. You see, it's minus 40 dB per decade, but then it cuts back to minus 20, so it's only got one integrator at down at low frequencies, whereas this has got two. But they can be made approximately the same, not quite the same. And then there's this one, which is probably the one I recommend for sort of motors and things, because when you've got resonances and stuff here, we're not dealing with motors, we're dealing with computational algorithms. So this has got minus 40, minus 20, minus 40. It's the one I mentioned earlier, and that's the one I used when I was showing you the two integrator method in LMS. This span ratio, the ratio between WH and W low, W high, W low, determines the phase margin. It's usually if that's about 10 to 1, phase margin is about 55 degrees roughly. If you make it lower, then you get a higher gain for a given bandwidth. Here, crossover frequency, you get a higher gain if you make it the span ratio lower, but in doing that you reduce the stability because the phase margin goes down. See, when you're comparing these algorithms, a mistake I think a lot of people make is because they don't look in the frequency domain, they don't compare like with like. You've got to compare with the same crossover frequency. Just like in here, if you are comparing these two systems, you must keep f phi, the crossover frequency, the same in both cases, and then you check it for like disturbance rejection properties and so on. So the speed of response will be the same for both of these. It won't be any faster, that one. This one has the ability to be faster, however, because you can increase the bandwidth a bit without running into trouble with the phase margin, whereas here, if you increase the gain, and in other words you come down at -20 here somewhere, then the phase margin, it'll cut here, let's say, as the crossover, and then the phase margin will be reduced. And likewise with this one, if the gain's not sitting exactly where it should be, you're in trouble either way. If the magnitude came too low, the phase margin would be down here somewhere. If it was too high, it's up here. So it does present a problem, even though it's interesting to check the theory that in fact that's how these algorithms do behave, just like a control system, even though they're time varying with so on. Yeah, as I've just said, that the gain crossover frequency determines the speed of response. And this is an really old paper here. You can do, with feedback, you can also do spectral factorization. I looked at that. Those of you that are into Wiener filters will recognize that. This is called a Lorentz series. I had a paper on that. Some other authors questioned the convergence of it, which was interesting. But it's like a lot of these things, like even in Newton's methods that you see, which have also got errors in them, of course, and an error term like in feedback, they're not guaranteed convergence either. So not all these methods are guaranteed convergence. But the LMS, of course, is, because it's provided you keep the gain below a certain amount. You can also do deconvolution, but it's not very successful either, because it doesn't take account of the noise in the system. It's for deterministic systems it works, but nothing's really deterministic, nor noise free. So this is convolution, and if you put the system in, if you do a mirror of the FIR filter here and put it in the feedback path, you end up with the opposite of convolution, because so convolution is in the feedback path, and you end up with deconvolution, which the control loop forces the opposite. Just like I said earlier, that whatever you put in the feedback path, if you can make it stable, you get the opposite, but you have to make it stable. You can make it stable quite easily. This is not a big problem to do that. You can do division. I'm just dividing two numbers here. This is scalar, B and A. So you can have a divider in with an analog. That you could put an op amp in there, for example. You can divide B by A. So what you get out of the integrator is B over A. You can define this as with a differential equation. The rate of change of output, because that's an integrator, so it's like the opposite of that, is K times the error, and the error is B minus A times W of T. So this is a function of going to be a function of time, because it's going to converge to some value, whereas B and A here are just going to be constants, but of course they can vary with time. So I could put B function of T, but here I'm just saying that. So the convergence point is, equilibrium point is B over A. It works quite well. You can do the same with gradient descent that I just mentioned, due to the Cauchy's method of the gradient descent. And if you draw a diagram, if you work it out and draw a diagram in analog, you end up with something very similar to the sort of engineering approach, would be B in there and A in there, but you end up with another A in here. So you've got two multipliers in the loop. And why have you got two multipliers? Well, it's actually slightly cleverer, the gradient method, because what it's done is it's allowed for a change in sign. here, for example, if B and A are both positive, that isn't a problem. Everything will be fine, provided you got the signs right of the integrator. It's negative feedback and so on. But if you made A negative, this loop would be unstable, so it wouldn't work. Or you made B negative, then I think the same problem. So yeah, I think it's the same anyway. Not sure. Whereas here, you've got two multipliers. It doesn't really matter what. Actually, I think B should be all right, negative, but A has to be positive here for it to work. If it goes negative, the loop goes unstable. Forgetting now. Anyway, here A must be. It doesn't matter what the sign of A is, because it just gets reversed back again with this second multiplier. That's quite clever. I think I have looked at this as well in more detail somewhere. I think it's in my book. You can use Newton's method, and you'll see that Newton's method turns out to be a control system as well. But it's got this is strange feedback from the output feeding back into the error, which you'll never see in a normal, well, at least I've never seen in a normal control system, but you might think it's some kind of nested loop within the loop. I suppose you can see it, but it's not got a summing junction, it's a multiplier in there. And that gives you, that's the fastest convergence because it's quadratic. That means the error goes down as the next, for every step, when it's in discrete time, that is, the error goes down as the square of the previous error. So if it starts with an error of 0.5, it goes to 0.25, 0.125, and so on very quickly. And you can extend this, of course, to higher order methods where it's a sort of extended Newton, where you can have quartic convergence and you end up with multiple loops and so on. But here we can investigate tracking with the gradient method. This is the control method, just with straight feedback. And this is division 1 over a time varying parameter. So this is the A term, is varying with time. It's got to be offset because otherwise it can go unstable with one of the methods. So I've had to make it always greater than 1, the A term. But just to see which is the best, it goes without saying that the Newton method here has the smallest error, the best tracking. You can see the Newton method's the blue here, and it follows nicely the so the true division, the true value of 1 over 3 plus cos 2 pi times 0.9k is this here, the red, and it's tracking it really well. The gradient method due to Cauchy is a bit slower. You see, it doesn't quite keep up with it with the Newton method. And the control method actually is surprisingly not bad. It looks almost as good, doesn't it? It shouldn't really be. The trouble with the Newton method is you've got to be careful of the initial conditions. If you don't start it off in the right place, it'll diverge. Whereas the gradient method doesn't care about that, and the control method doesn't care. But the Newton method should generally give you a lower. You can see it is a lower error. So when you've got time varying inputs and things, that's when these methods come into their own, and when you can see another way around solving the problem. Not when everything's constant. It's just the classical mathematical approaches, and you use the usual methods. But in a lot of engineering problems, we're dealing with situations, let's say with matrices that are varying with time, due to inverse kinematics and whatever. You're trying to inverse matrices. Mathematicians have a fit when you say you're trying to inverse a matrix, even though they've developed all these methods for inverting matrices. The last thing they want you to do is invert a matrix, especially when you're solving a set of linear equations. They prefer other methods. To direct inversion is considered a big no-no, but engineers perhaps don't agree. So we can do the same. We can invert a matrix using feedback, which is quite interesting. So instead of 1, this is an identity matrix going in here. It's actually an error matrix here. We've got our multiplier feeding back, and these are an array. It's a diagonal array of integrators. as many as the order of the. So if there was a 2 by 2 matrix, you would have a 4 by 4 matrix with 2 integrators on the diagonal terms. Sorry, yeah, 2 by 2 matrix, I beg your pardon. 2 by 2 matrix with, on each of the diagonal terms would be a single integrator. So it's z to the minus 1 over 1 minus z to the minus 1i. The z to the minus 1's for physical realizability. In a discrete control system, you need at least one step delay between the input and the output. You can't, a computer can't respond instantaneously. It needs at least one sample. I mean, it might seem instantaneous to you, but it's not like analog. You could do the same with analog. You can also take the square root here of a matrix. I've written a paper about that as well, where you put a multiplier. You multiply, here you've got a matrix X, and W should converge to the square root of that matrix. And again, you've got a, instead of here in the Newton method, there's no step size, because the Newton method doesn't kind of need a step size. It's kind of optimized. It just doesn't need one. It's kind of unity step size. But for the this method that I developed, well, it's just a straight square in the feedback path, like the square root function we saw earlier, but with a matrix. So we get W squared, so it's W times W. It's not W times W transpose, it's W times W. And you end up with an error matrix. And so W should converge to the square root of the matrix. So the sort of concluding remarks is that feedback has been used in mathematical algorithms since the 19th century, but people, I don't think, have really recognized it as a control system. You see an error and you think, well, it's just an error, but if you look at it from a different point of view, it is a control system. So recognize feedback when you see it, because you see this type of algorithm, WK plus 1 is WK, that's got negative feedback, which is recognizing a forward path integrator or integration. It can be arrays of integrators, as we've seen, and it's possible to compensate a little bit at least. And it's perhaps more important than it looks, because, say, a lot of modern algorithms use these kind of approaches. We'll see gradient type algorithms emerging, which are based on gradient descent, some quite sophisticated ones, and they're all got the same kind of thing. They've got an error, they've got an integrator in the forward path, and you can treat them like a control system, and you can compensate them. You can take it to the next stage as well. You can look at it as in an engineering sense at the bandwidth of the control loop, perhaps even as well, which I was doing with LMS. And you can therefore, when you increase the step size, instead of saying I'm just increasing the step size, realize that what you're doing is you're increasing the bandwidth of the loop of the integrators, and therefore that makes it faster if you look at it from an engineering point of view. So there's a number of insights there, which I think is quite interesting in any case. So thank you very much. Bye bye.